Here's on a continuing video for ME401, and we're going to introduce the numeric solving, some dry stuff. So I try to see as I do my preliminary walkthrough how I can try to make it engaging for a class that doesn't necessarily have a computer in front of them. What we're really trying to do is trying to understand what a Newton-Raphson does. Its implementation can be pretty straightforward, but it looks like just like a mysterious hitting a button and get the solution. Let's try to make sure if we can understand it. Okay, so I didn't make this into a useful PowerPoint where I could go animation for the thing, but I think it would be very wise to attempt to do that. So let me pause my video for a second and see if I can fix it. Use this animation in PowerPoint to make it a little bit less of a boring little trip. So here's the big idea in a Newton-Raphson. We guess, we evaluate how wrong our guess was, and then we project using a slope to figure out what a new guess would be, and then we repeat, right? So we try to refine our guess, and hopefully we're looking for convergence. That's the numerical analysis technique, and almost all numerical analyses kind of do that type of thing. We try to make a guess and we figure out what's wrong. So let's say that the guess was some value, and we have let's say we have a function, right? We have a function that's a function of x, and we're trying to figure out what the solution of y is going to be. So we plug in x, and we get the thing, right? We get a result. We don't know. I should say it again, right? We know that this function exists, right? And we know there's going to be some solutions to the function. We don't know what they are yet, so we try xi as our initial guess right here, and we come out and we find out that we don't have it. Like let's say we're going to find the roots of something, right? And we're going to try to find, is this first guess a root? And you try it out and you find out no, it doesn't equal 0 right after we put the thing in, so it's obviously not a root. So we say, well, let's take the next guess, and what we'll do with the next guess is we're going to take the first guess and we're going to subtract out a division of what we just did divided by if we took the derivative, right? So that really is what we're saying, is we're taking the slope of the thing, right? So it's not really quite obvious what that means until you start trying to use it, right? So another way to write this out is to multiply that slope out over to the other side. So we'll subtract out the initial guess from the next guess and multiply it by the slope right there. And we set it up into an equation right here where we have the slope times the difference between the guesses is going to be equal to the negative function, right? Well, it just sort of turns out that way right there, right? And you can see where the negative comes from is the fact that we are flipping that x. We're taking the difference between the initial guess and the next guess right there. So we flip what the order was going to be. So that's where that negative comes from. And what we would like to do in this operation is to make the difference between the guesses get smaller and smaller, or very small. So here is this one-dimensional example right here, and it's one-dimensional because it's coming in. It's just really just one variable that we're dealing with, and that's going to be x. And we want to find the roots of this thing right here, right? So we have this x. It's a cubic, so we know there's going to be 3 roots. So we have to know that there's going to be 3 different possible answers where y is going to be equal to 0 for an x. That's going to give us a y equals 0. And from Wolfram Alpha, we could just plug this thing in, and we could find here are the answers, right? So I have to be careful when we make an initial guess, just like we had in the Excel, that one of them, our initial guess might be close to one of these, so our convergence might send us over to that other spot. So here's the graphic of this, where we're using an initial guess of 1.8. And we're going to see, and I'm going to walk through this using values, using numbers. Now, they didn't quite do this in the book, but I think it will help, right? So this really helped me to try to digest this technique and walking through this. So that's one of the reasons why I'm creating a video for it. I'm also trying to practice for class and see if I can make my delivery of this material maybe a little bit better. So here's my initial guess of 1.8. You can see, and you can see that when I plug it in, here's what the actual curve looks like right here. That I hit a point y1. And so what we're going to do now is we're going to make a new guess by taking and finding the slope, right? So we presuming here we're able to find the derivative of this thing right here, and that we can take and use that and enter that same x value in for the derivative of y, so that would be like y prime. And we're going to say, okay, so what do we get when we find that? Like, okay, let's put in this at 1.8, and it's gonna land. It's gonna converge. We're gonna find a new guess over here of x2, and then we're gonna put x2 in there, and it's gonna hit a new point right here, and we're gonna find this new answer, right? So that still is wrong. But what we're going to do is we're going to take the slope from there. So we're, again, taking the derivative and plugging that guess back into the derivative. So we find a slope and projecting. So we have a third guess, x3. And we're going to see that gets pretty close to being the right thing. This graph over here is an example where we have 2.5 is the guess, and you can show that it converges at a different number. Where this one, the guess at 1.8 converges to this answer. This guess at 2.5 converges over to this answer right there. So here's my step-by-step of this. Let's hope it comes in eventually. Oh, okay. So here's initial guess. We plug it in there, and we get 137.7, which I write, which is not 0. That's true. And then we find the slope at this guess right here, right? So we have the derivative of that function, and we put the 1.8 in, and we get 33.08. Then we find the intersection of the slope at that point right there, right? So that's going to be, the intersection is going to be x1, right? That's the value that we have here, minus, and then we find the slope that's of this thing right here. So we have 137.7, which is what the y value was going to be, and divided by the slope right there, and that gives us a new value of negative 2.363. I was thinking I should make this this curve in Excel and animate it that way. That would be maybe that would be a good way to do this. Maybe, I don't know. Anyway, we could do that. So anyway, I find my delta. Here's my delta for my guess. My delta is not good. So my new guess. Okay, so this was the new guess. All right, so this is the delta we want to minimize. But here's my new guess. We already established what it was. We stick this back in, and it comes out to negative 56.12, which is still not 0. So once again, we're going to take that initial guess, and we're going to put it into the slope. Now we find what that slope is, and we find this intersection point, x3, by taking the initial guess, subtracting out the value that we got from the function divided by the slope right here. And here is our next guess. Here's x3, our new guess. And our new guess, we find what our delta is. This is the thing we want to turn into 0, right? So we want to minimize that. So the new guess is that value that we got for x3, and we plug him in, and we find that we get 6.554, which is still not 0. So we plug in that guess that we had, that x3 guess, and we get this new value of 50.93, and we do this for the, we do the thing again where we take the value and divide it by that slope. And now all of a sudden here is the difference between our two guesses. We got closer and closer. So here's one more with the new guess. We plug it in and we're getting very, very close to 0. And we find the slope, we plug this back in, and look, we're getting the same value right now for our new guess. And if we make sure we keep our sig figs as we put throughout the thing, we can see that this is now wicked small. So that's how that is the Newton-Raphson. That is what the Newton-Raphson does. And we have to decide that we have to establish a tolerance when that's going to be good enough. I mean, on a computer, this is going to go real fast, but it could go on forever, you know, in terms of we might not have the perfect convergence, so we have to have some type of internal tolerance that says, nah, that's going to be good enough. So if we want to do this, and let me see if I have how much time I took up there. That's like 11 minutes. I think I'm going to break this up, right? So that's part 1 of the thing.